So this is the graph between wavelength and spectral radiance. So as per the classical theory, you can see that the graph is pointing like this, and the actual value is the theoretical value or the experimental value is like this. So these two things, I don't think they do match. So the equation that explain this observation, as per the classical theory, this thing doesn't comes over here. But if you hit a metal, you see, as you increase the temperature, it absorbs the energy and it changes its color. So this thing doesn't match with the classical theory. This is the observation. This is predicted according to the classical theory. Here you can see something like it's a metal of metal iron that is being heated, and you can see the color. So different region of color, uh, different region of color, or different color or different wavelength of light uh, show the temperature of different places. Here this color is different, so the temperature at this space is different. Here the color or the glow is different, and the temperature is different. So blacksmith use this thing, and again you can see the color defines the temperature. This color defines the temperature is greater than 1300 degrees Celsius. You can see here is the Fahrenheit, here is the degree Celsius. So this color represents 550 degrees Celsius. So this graph is for steel. If you hit the steel, if you see this color, gradually the color will increase, or the color will become from darker to a lighter one. The more lighter color you see, the more temperature it has. So that means the color emitted by the body or by the steel when it is hot is, is exactly like mm, can be related to the temperature. So similar concept can also helps to measure the temperature of the lava flow from its like color. That means by observing the color itself, we can predict the temperature. Here, the temperature, as the color is like this, you can see the temperature will be around 1200 degree Celsius. This is our electromagnetic radiation or background radiation of our universe. So now again coming to the same same question, the theory, classical theory predicts this, but actually at 5000 Kelvin we observe this color. In this wavelength, the color, like in this wavelength, this visible wavelength, we see the this color, and classical theory predicts this thing. So which is infrared region we can't see, but as we have seen here, we observe colors when we hit something. Here we took the example of steel. So we are observing this thing in practical, because we are hitting it when observing the glow. But the what the theory predict, the infrared region, the wavelength is in the infrared region, we should not be able to see, but we see this thing because it comes under ultraviolet visible, sorry, it comes under the visible spectrum, which is the observed value. So here the classical theory fails, and Max Planck used the concept of quanta or quantum of energy to explain this. So that is why uh, he, like Max Planck, is called the father of quantum theory or quantum computing. So what he suggested is that he suggested that Max Planck proposed the hypothesis that energy is radiated and absorbed in discrete quanta, yielding a calculation that precisely matched the observed pattern of blackbody radiation. What is the observed pattern of blackbody radiation? we have seen over here, we have seen this is the observed pattern, this is the prediction of classical theory. Here it fails, but once you apply the equations and you get the exact value or precise value that matches the experiment as well as the theoretical calculations. So according to Planck, quantities of energy could be thought as divided into elements whose size would be proportional to the frequency. So here E is equal to h into lambda, and here h is for the Planck's constant. So energy is directly proportional to the frequency. So in actual practice, Planck's law of black body radiation can be explained using these equations, which is like beyond the syllabus of class 12, beyond this level class 12. So I hope you can understand. Still, Ayan, if you are further having any doubts, you can ask.